All right, so we're talking about section 2.1, and in this chapter, we're going to talk a lot about graphs and transformations, stretching, compressing, and section 2.1 focuses mainly on symmetry and increasing and decreasing. All right, so we're going to take a look at this. We talked a little bit about continuity before. So here in these 2.1 notes, so a function is continuous over an interval of its domain. If it's hand-drawn graph over the interval can be sketched without lifting the pencil. So it's going to have continuity and continuous if I can trace that without picking up my pencil. So then when I have something here that that has a point of discontinuity, okay, I can't follow that with my pencil, then that means it has discontinuity and it's not continuous. Now, the whole thing is not continuous. However, this is continuous from here to here. So if I wanted to write this down, well, where is this continuous from? Remember, we always talk about the domain when we're talking about this. So we start over here at negative infinity with a parenthesis, and we go all the way to here, and it stops being continuous, at positive 2. And it's not included there. So if we look at this, this is saying that this is not continuous from here to here. So let me write that down. Thought I had it over here. So this would not be continuous from negative infinity. I mean, it is continuous from negative infinity to a positive 2. Okay. And then here, it's continuous from 2 filled in to positive infinity. And then over here, let's look at this. Well, this is continuous, this part of it, then it disconnects, and then there's another continuous part over here. So it is continuous from here. So where's this negative infinity? To where it's going to go and never cross this line. This is called an asymptote, and it never crosses this line. We studied this in chapter 5. So it just gets closer and closer and closer, but never will touch this asymptote. It's undefined here. So this just gets closer and closer and closer to 2, but we use a parenthesis because it never touches 2. Okay, or this is an or sign, and I didn't really use that over here. I should have probably put the or sign in there. Or it's continuous from here, which is 2 to positive infinity. All right. Now, if I look back up here at this, this is continuous. Okay, so that domain is going to be from negative infinity to positive infinity right here. All right, so let's take a look at this. The following function has a point of discontinuity at x equals 3. So notice it has an open circle there, if you can see this, at x equals 3. So it is continuous, though, from here to 3. So we would write that it's continuous from negative infinity till it gets to 3, and then it stops with a parenthesis, and it's an open circle, so from 3 to positive infinity. Down here, we have an asymptote at x equals negative 2. So we're continuous from negative infinity to 2, right here, and then from 2 to positive infinity. So it's just writing those domains, okay? So that's continuous and discontinuity. All right, so let's talk about increasing and decreasing functions. So to decide whether a function is increasing or decreasing, let me just try and, there we go. Increasing or decreasing or constant. So now notice we're talking about here, when we talk about increasing and decreasing, we look at our range values. So remember our range values right here, that means we're going to look at our y values. So if a line or a function is increasing, then the range, that means the y values are increasing from left to right. Okay, so the graph rises from left to right. If it's decreasing, then your y values are getting smaller from left to right, and the line falls. So let's kind of take a look at this right here. So you notice as this grows, right, my y values are getting increasing from left to right. So that's an increasing line. Here, my y values are getting smaller, and it slopes down from left to right. So that's a decreasing. Now, sometimes they don't increase or decrease, and they just have a constant. So that's what this would be here, is just a constant. Never changes. So let's take a look at this. So I don't want to pull it all the way up because I don't want you to see the answers on this yet. But okay, so let's take a look at this. Whoop, right there. And notice here, I want you to tell me a little bit like, where is this graph increasing and decreasing? And don't look at the arrows, because the arrows looks like, well, it's pointing up, so that means it's increasing. But you know what? If you look at your Y values on this, they are getting smaller and smaller and smaller, right? And it's going down from left to right. So that means this is decreasing. And so think about, where is it decreasing from? It starts over here, negative infinity, and it decreases until we get to this point right here, which is 1. Remember, we talk about domain, when we talk about increase, decrease, we write that interval in our domain. So to 1. So that's what we have here. Decreases from negative infinity to 1 with a parenthesis because it's an open circle. All right, now what happens here? So let's go to this part. Well, now my Y values are getting larger, so that's increasing. So where does it begin? Well, it begins increasing at 2 for this part, right? Because this is not a continuous function. So this part of it, it starts increasing at 1 with a bracket. And where does it end? It stops increasing right here at 3. So from 1 to 3, we see that that's where it's increasing. All right, what about this last part? Well, it just stays the same. So that's your constant. So where does that begin being constant at? Well, at 3, and then it goes to positive infinity. I'm sorry, yeah, from 3 to positive infinity. Okay. Now I want to clarify something on this. I just saw this on the notes here. This should be a parenthesis, and this should be a parenthesis. Now, when you use increasing and decreasing, we don't put brackets in there, and here's why. Because this is connected. Now you can if it's not connected like this. So I can begin this with a bracket because I'm beginning it. But here's the problem. If I go here and I'm saying, okay, it increases to 3, and 3 is included in it, so it's increasing at 3. But then I'm also saying it's constant at 3, and that's included. Well, it can't both be increasing and constant at 3. It has to be one or the other. So we don't include it when we say it's increasing, and we don't include it when we say it's constant. So that's why if we have a continuous function, we're not ever going to see a bracket when we talk about increase and decrease, because a point can't increase and decrease at the same time. But because this is discontinuous, I can begin, this is a whole new one that I'm beginning, so I can begin it to include 1 on that part of the function. All right, so let's take a look at this. So this one, remember this is the same thing as y equals. So this is like y equals 2. Okay, so y equals, b just is whatever your number is there. So this is just a constant. Well, what is the domain of that constant? Well, it goes this way forever, it goes this way forever. So our domain is negative infinity to positive infinity. And it's also continuous across the entire domain, meaning you don't pick your pencil up when you trace it. So here, this is saying, all right, well, tell me where this decreases. So let's begin telling me where it decreases. Well, the y values get smaller as I go here. The line goes down from left to right. So it's decreasing. So it's going to start over here at negative infinity because this arrow goes on forever, right? It's going to decrease all the way down, and then it's going to stop at 0. And that's an inflection point, and that is going to then start to increase. So let's write, it's going to decrease from negative infinity, and where does it end? On the x-axis at 0. So it decreases from negative infinity to 0. And then it increases from 0 to positive infinity. So then it increases from 0 to positive infinity. And notice both of these have parentheses on it, right? Because 0 can't both increase and decrease. So we can't include it in either one. But when I look at it this way, when I talk about it being continuous, yeah, it's continuous from negative infinity to positive infinity. That never have to pick a pencil up if I trace that. So it's continuous on the domain negative infinity to positive infinity. Okay, this is increasing, decreasing. This is just the whole function. Now let's talk about symmetry. So symmetry means if I take it and I fold it up, it's going to be exactly the same on both sides. So if I have a function and it's defined by f of negative x equals f of x for everything in this domain, for all the x values in the domain, then that means there's symmetry with respect to the y-axis. So I'm going to come back to this, but what I want you to remember on this is for symmetry. Let me get my notes here so you can see what I'm doing. I just have to kind of readjust my camera so I'm doing it right here. Goes this way. There we go. All right. So if I want symmetry, I'll just put symmetric to the y-axis. Okay, that means if I put a negative x in for x in my function, then it comes out to be what the original function was. And I'm going to show you that example in just a minute. All right, but one thing I want to tell you that if I have a point on my graph, and let's say it's point AB. Okay, so like right here, I have this point AB. It's kind of hard to see. Here's point AB right here. Shoot, I don't think you can, maybe you can see that. This is point AB. Well, it's going, okay, I'm gonna have to, I'll draw it here for you. Okay, so let's say we just have this function here. All right, so if this is point AB, then that means if this is symmetrical over the y-axis, I can fold it over, right? Then this point over here is going to be negative AB. So if AB falls on it and there's symmetry to the y-axis, then the x value just changes the sign. So this is 0.21. So this point over here, I just changed the x value, is negative 21. So to see if there's symmetry to the y-axis, you would change the x value, just the sign of the x value, okay? And I'm going to explain this in just a minute. I'm going to come back to that in just a minute. So let's look at this one here. Okay, so here we have symmetry to the origin. So if I put a negative x into my function, and I can simplify it by pulling a negative out and ending up with the original function, then the graph has symmetry with respect to the origin. Now I want you to kind of see this. It's kind of hard to see, but here is AB. And this is like a rotation, 180 rotation around. That's what symmetry around the origin is with respect to the origin. So if I have point AB on it, then I'm going to have point negative A, negative B. All right, so with respect to the origin, so if it's symmetric to the origin, then if I put in a negative x, I would be able to pull out a negative and then have my original function if I pull a negative out of there. Now if I look at points, oh, sorry. And now if I look at points on there, if I have point negative A, negative B, then the opposite of that, of both of them, are going to fall on that same function. Okay. All right, now last one, and we don't use this one very much. If there is, I'm going to put it down here, if it's symmetric to the x-axis, that's when we start talking a little bit about maybe some hyperbolas and things like that. So here is the graph. See how it goes? It's like a sideways parabola. I mean, it's still a parabola, but it goes to the right. So it just means that if I have a point AB, if it's symmetrical to the x-axis, then the y value changes. Then it would be A, negative B. That point would also fall on the graph. All right, so here's something you're going to be asked to do. So determine if this has symmetry with respect to the y-axis. So what I'm going to do, so does this have symmetry to the y-axis? So that would be a question that I would ask you, and you'll be given the function. Oh, there's a 3 there, shoot, minus 3x squared. Okay, so here, this is a minus 3x squared. Sorry, that's kind of hard to see, and I'm using a pen, minus 8. So I want to determine if it has symmetry to the y-axis. So I'm going to go ahead, I'm going to see if I put in a negative x, gosh dang it, if I put in a negative x, that my function comes out to be what it was originally. Okay, then if it does, then that means it's symmetrical to the y-axis. I don't know anything really about the points so much, but I do know that I'm going to put in a negative x. All right, so that's what this means. So let's put in a negative x. So here we have, if I put in a negative x, I'm going to show the work by doing this. Okay, substitute in a negative x. It's always a negative x that you're going to put in there. Because if it's the y-axis, it's the opposite one we put in. That's why we're putting in the x. All right, so enough of that. So I want to simplify this. So if I simplify that, would you agree that negative x times negative x times negative x times negative x becomes a positive x? Anytime you take a negative to an even power, it's going to become positive. So then we have a minus 3, and this is a negative x times a negative x, so that's going to be a positive x squared minus 8. Well, look at what we ended up with. Did we end up with the same thing that we started with? We did. So the answer is yes. It has symmetry to the y-axis. So that means I can fold it over the y-axis, it will be the same. All right, so how about this one? Does this one have, to the x, let's go to the origin. So to the origin. So here is the function. Okay, now what I want, if it has symmetry to the origin, if it's symmetric around the origin, I want to put in a negative x, and then I want to be able to, when I get done, pull a negative out of my answer, and then this is what I started with. So let's see if I can do that. So let's put in a negative x. So if I do that, okay, so I just substituted in the x with a negative x. So this is going to become a negative. If I take it to a third power, negative times a negative times a negative, that is a negative. Okay, and so this minus, and then what does this become? Well, it's an even power, right? So, you know what, I wrote this. Okay, that's okay. So I wrote this, I'm sorry. So this is going to be a positive x when I bring it out. So what happens if I take a negative? This is not my original. It's not my original. And if I take a negative out of it, that pretty much just changes these signs. It's still not the same. So no, that does not have symmetry around the origin. It also doesn't have symmetry around the y-axis because it didn't come out to be exactly the same. So it would be either one of those. But let's look at one that does. So let's do another example because I actually just wrote that one wrong. So let's look at this one. Okay, here we go. All right, does that have symmetry to the origin? Well, let's check it out and see. So we have negative x to the third minus 4 times a negative x. Just put a negative x in for each of these. So this is a negative x to the third. This becomes a positive 4x. Okay, so it's not the same as the original, so I know it doesn't have symmetry to the y-axis. So let's take a negative out of there. So if I do, that becomes a positive x to the third. This becomes a negative 4x. Okay, so now I have a negative, and is this the same as the original? It is, and that is what this means. I put in negative x, I can pull a negative out of it and have my original function. And if that's the case, then it has symmetry around the origin. So yes, it's symmetric to the origin. So it's just putting a negative in there to determine. Now I'm going to give you just a little bit of a hint on this. So let me first of all go through this with you on even and odd functions. All right, so a function is called an even function if I put a negative in and it comes out to be just that original function. Well, that's exactly what we talked about when we talked about being symmetric around the y-axis. So if it has symmetry with the y-axis, it's an even function. Okay, if I can pull a negative out and have the original, then that was symmetric to the origin, right? Then that's an odd function. Now I'm going to give you a way to kind of just look at that. Now I showed you how to do it by putting in the negative x. That's, doing it by hand. But honestly, if you just look at the problem and I go, okay, well, if I put a negative in for an even and I put a negative in for an even, it's just going to come out to be positive. So anytime I have an even power, it's not going to change anything because it comes back to be positive. So this, here's a pencil here. So this is going to be even. Oh, pencil doesn't work. This comes out to be even. All right, now I have an odd and I have an odd. So that means it's going to change the sign, right? Because if I put a negative x to a third power, it's a negative. And I'm just going to show you this. So that would be a negative 6x cubed. If I put a negative in here, that's going to be a positive 9x. So I can take a negative out and it takes it back to the original. It's kind of hard to see, I'm sorry. But what that is saying is that if these are both odd, then it's going to have symmetry with respect to the origin. If they're both even, it's going to have respect to the y-axis, so it's an even function. Now, you can't just go, oh, well, if the powers are even, then it's going to be an even function and powers are odd, because you might run into one like this that has an even and an odd power. Well, if that's the case, then it's not going to have symmetry. It's going to be neither. Okay, it's going to be neither. If it has an even and an odd, it's not going to work out. It's like this one that I did right here, right? When I did this problem, we had an odd and we had an even, and it didn't come out to fit either one of those criterias. So if they're both odd, that's respect to the origin, and it's an odd function. If they're both even, okay, they're both even, then that's respect to the y-axis, and that's an even function. And we'll look a little bit later about what even and odd functions look like. Now, what do you think about this one? What if I have an x plus 1 squared? Well, you might look at that and think, oh, okay, well, it's squared, it's even, so that means it's going to be an even function and have symmetry around the y-axis. Well, not really though, because if you really, this is really saying, let me put this on another sheet of paper so you can see it. If I do this, all right, you might think it's even because it has an even power. However, this is saying take this times this. So if I multiply this through by either distributing a FOIL, however you want to multiply it, we have x times x, which is x squared, plus 1x. Okay. And then we have 1x plus 1. So if I multiply that through and I combine these like terms in the middle, that's what it is. So now let's look at the powers. Well, I have an even power and I have an odd power, so what's that going to be? It's going to be neither. But if I would have looked at it here and just automatically assumed because it was squared, then that would have been wrong. So you have to be kind of careful. It's not just because it has an even power doesn't always mean it's going to be an even function. Okay. So even functions have symmetry around the y-axis, meaning I can fold it over the y-axis and it'll be the same. And odd functions have symmetry about the origin, which means I rotate it 180 degrees and it lies on itself. Okay. Just a little bit of information on even and odd. All right, so that is all that I have for you on section 2.1. So I hope that was helpful and that you have a fabulous day. All right, have a good one.